My name is Eric Ferreira. I've been working in Amazon for about 14 years. I've seen everything you can imagine around there. And when I'm preparing for this talk, I have a very specific things I want to talk about some new product or new feature we announced. But since we haven't announced yet, I couldn't name the talk with that. So that became Innovation at AWS. And it was a good opportunity for me to figure out how I can talk to you how those innovations, those products, and each one of those services you know about on AWS, how they happen, how they come to be. First, on AWS, we inherited from Amazon.com their same idea of having a flywheel, where you focus on things that remain the same, interact over them, and get better and better. So in case of Amazon.com, we talk about price, selection, delivery, and you make them better and better, and more people and more products and more things. And we've done that. So in AWS, we apply the same idea. So I'm going to talk to you about specific about Redshift and some new features we added to Redshift, but how this happened. And I know very well because I'm the first person that worked on Redshift. I work on the proposal to go with Redshift. So it's like a child to me. So I'm not a sales guy. I don't talk about sales or prices, anything like that. But if you say anything bad about Redshift, I take personally. Okay, so anyway. So first thing we had to keep in mind for a service on the cloud was to have to adopt a retail mindset, right? The customers have a choice to come and go as they please. So we have to delight them and want them to stay 1 hour at a time, right? You can come in, you can play, and I don't like it, I'll go away, right? And most of the products, it's very easy to come in and very easy to get out and pack your data and go somewhere else. So we have to win the customer every hour of every day, right? And the way we do that is anything we do in Amazon, we start with the customer and work backwards. Right? We figure out, okay, what the customer needs, what can I help the customer, and then we work backwards to how can I delight my customer with whatever I'm going to do. So we figure out what customers want, right? What problems they're facing. Is my product going to alleviate their pain? We can do it better than everybody else? There's a reason to do this product? There's a need for it, right? On the data warehouse area, right, in 2010, which was a long time ago in Amazon years, there was pretty much no option of data warehouse on the cloud. There's barely a cloud then. We're just starting. People are starting to, hey, now I have a lot of data. How can I do my work? And the problem was, it was complicated to install, maintain, operate, required large upfront payments, was too expensive, and always running out of capacity. And even those startups that started with us on the cloud, they say, now I have to get my data from the cloud back to on-premise so I can do ETL and do business intelligence. Well, can you help me? Can you do something? And they're trying to use online databases for like RDS MySQL to try to do reports, and it goes so far, right? It works well up to a certain point, and then it's too big for that data, and the queries are too complex, and they are not happy about that. So the one thing we do in Amazon for every single product, every single idea that comes out, we start by writing a press release saying how we're going to announce this product when it's ready. If we get the funding and if we spend the 2 or 3 years to build the product, when we announce, how we're going to announce this product. We start there. How we're going to think, like, why the customer is that something that's new-worthy, right? What's the difference it's going to make on the market, right? Another thing we have to do is FAQ, a list of frequently asked questions about how that can help the customer, how that will help. And those documents actually become the release notes and the frequent asked questions when you launch a product. But we do that before we have a product. That's how we focus our attention on what we are going to deliver to the customer at the end. So for Redshift, that took about 3 years, right? And we do that in the 2 pizza teams in a way that we have a small group of people that owns the project beginning to end. We don't respond to anybody else. We own everything beginning to end. And that's why you might see lots of different products on AWS that kind of, there's a lot of, well, there's overlap here and overlap there. Why do you guys let the overlap happen? Because the teams do what they want to do for their customers. And there is inevitable there will be some overlap. Over time, we can optimize things and put things together and make a single solution, but it's inevitable that you have different products that look, well, so what's the difference between this product and this product? They're kind of similar, right? And there is a difference, trust me. We have a set of customers and requirements for one of them, and an FAQ and a press release for one, and a set of requirements for the other. So the way we do in Amazon is we build a team, and that's what I did in 2010. We built the product, it took about 3 years, and we launched internal beta, private beta, we launched, and then we iterate on it. We launched something that's not fully 100% ready with everything we wanted to be on there. It has enough for that release note we created in the beginning. And iterate is the key word for us. We change a lot, we iterate a lot. Redshift has a new version of the database every 2 weeks. And we add features that matter to the customers, we raise the value, more customers come in, we get their feedback, and add more features, etc. There's a tricky question you do when interviewing product managers, is like, who owns the roadmap for Redshift? And so the product manager owns, like, no, the customer owns the roadmap, you just manage it, right? And that's how it is for every product in Amazon. Since we launched, we have over 120 different significant features added to Redshift. Right? And always the price always being the same. So that's the part we iterate. Every 2 weeks there's a new version, some new features, some bug fixes, etc. And with that, pretty much every single product on the AWS big data catalog has pretty much the same history behind it. A team of people, two pizza team got together to solve a customer problem and decided to launch something. So every single one of those you can imagine. Today, there was a talk earlier today about Aurora. There was a talk earlier about Glue, right? And all the teams the way it happens is the same. And you can see on the collect side, right? You have a number of process kinesis and IoTs and direct connect to get your data in. The migration service that you kind of cool product is going to come, I think, after this talk. Don't miss it. On the storage side, you have S3, Glacier, DynamoDB, and Elasticsearch, and pretty much all the RDS database you can imagine. And then you can have, on the analyze side, EMR, Athena, machine learning, Redshift, EC2, if you want to have your own database, Lambda, and QuickSight. And of course, each one of those have their story, their customers, their focus, and we own our destiny beginning to end. Now, I'm going to focus on a few of those that make sense for what I'm going to talk about, right? So the first one is Amazon S3. It's one of the oldest AWS services. It's just to store everything, right? And it's have an unbelievable high durability, and you can store anything. Has a huge bandwidth for scalability. It's really cheap, supports encryption, and it has become the backbone of pretty much every single AWS service. Every service can read or write to S3. So that's how we do things around. And the new idea, the new buzzword on the market talking about data lake, right? S3 normally is the place where the data lake resides and the data lives. You can land your files there and you can access in a very effective way. The other product I want to talk about is, of course, Redshift, right? And I used to talk about being like a petabyte scale relational MPP database. It's a real database, has ACID, has transactions, all this kind of good stuff. However, the feature I'm going to talk to you about also allows us to scan and select exabytes of data that lives on S3 directly on the data. It's called Amazon Redshift Spectrum, which I'm going to give you some details later. Right? But anyway, it's a fully managed database. So it's a service. It's not a database per se. It's a service that you can choose SSDs or hard drives. There's end-to-end security, fault-tolerant, backups, and cross-region replication of data for restores. And it's cheap, right? Pretty much it's cheap. So for Redshift, what we did was we started with a Postgres database. That's where we started. Open source, it's an open source, open base, we'd call, right? We started with a Postgres database. We removed the storage layer from it and replaced it with MPP storage layer with an OLAP SQL processing so you can understand those very complex multi-page SQLs. And a columnar storage, and the columnar will become clear why in a few moments. But that's what we did. That's the database, right? That's where we started from. But again, we wanted to make a service for the customers. We wanted to have automation like RDS, right? You wanted to be RDS for this database. And we did that. And using other AWS services so we can use that. So you don't reinvent the wheel, at least not all the time. Sometimes we do, but not always. So we use simple workflow, VPC, IAM, EC2 as our hosts, as our EC2 hosts. We don't get any special hardware by anybody. We use EC2 like anybody else. We use S3 for storage of backups and getting data in, KMS for key management, Route 53 for the elastic IPs and the DNS endpoints, and a CloudWatch for monitoring. And those services all together is what makes Amazon Redshift. And we launched, and it was pretty cool, and we had huge adoption in the beginning for a bunch of startups, and then enterprise customers came, hey, I want to use this because it seems to be fast and it's cheap, I want to use it. And we iterated and make it better and better every time. Now, what is the architecture of Redshift? We have a cluster that is a shared nothing cluster, which your data gets distributed around here. You have a leader node that have the SQL endpoint. You connect to the leader node. You don't connect to the compute node. You just connect to the leader node with a JDBC, ODBC, or pSQL connection, or plib connection. And here is where the data resides. Local drives, storage columnar. So every column is a separate file, in a sense, is a stream of blocks, but it's like a file. And all the data at speed, at scale, comes in and out of Redshift via directly to the compute nodes, fully in parallel, from S3, DynamoDB, EMR, or any SSH host you can put your hands on, right? So it is a share nothing, like brute force, let's divide and conquer to get those large data sets to scan, right? And that's what we did. Now, hello, there you go. The one thing we learned very quick is that brute force takes you some places, but it only takes you so far. At one point, if you just say, I don't want to deal about the data, I want to do anything with the data, just throw the data in, spread, and as many servers as I can, and then run in parallel, brute force, that works up to a certain point. When you get to the scale of things we do in Amazon, that's not enough. It would take like all the hosts in the world to run some workloads, and it's not viable. So we had to get smart about avoiding doing unnecessary IOs and unnecessary operations, so we don't have to only use brute force. We definitely use brute force. We welcome it, the idea, but it has to be a smart way of using that. And what we did is, first thing was the columnar storage. On a regular database, and all databases at that time, or most of them, or every commercial database at that time, a row has all the columns together. So when you read a column, you have to bring up a block that has all the columns together. So in this example, if you create date on this table, you will have to read the blocks for AID, blocks for location, blocks for date, right? On a columnar database, you only open the date file and you just read that. You don't need to touch the blocks of the files that you're not reading. That makes a huge difference for BI workloads. For OLTP is a nightmare. I understand that. This is not for OLTP. This was designed for business intelligence, for OLAP queries, for large reports, that you have very wide tables, but you don't query all the columns all at the same time. You just query a few of them, and that makes a huge reduction of I/O. The second thing we did was compression. Compression is good. Compression makes things smaller. Great. However, if you have everything on the same block, compressing numbers with characters, not always is the same algorithm is better for both. Because every column is a separate file, in a sense, we can compress different columns with different algorithms, so we can take advantage of the best compression for that data type. And if you know the data type, it's even better. You know that run length is going to be better, or Z standard, or LZO, or whatever is going to be better for you. What the system helps is you can run a command in the system on your table, and you can get every column, compress every possible way, and tell you which one got smaller. And then you can say, hey, okay, I will compress with that. And that, everybody agrees that compression saves space. But I will venture to postulate that compressing data also saves time. Because on data warehouse applications, most of your bottlenecks are related to I/O. So if you reduce the amount of I/O you have to do, you save time as well, not only space. The amount of CPU you will spend more because you have to compress and decompress data, it's not big enough to compare how much speed you spend or you gain by not having to scan everything. So it's a huge win in terms of performance. And we have benchmarks that you can get things three times faster just because you compress your data. The third one is something at the time unique to us, and now there's in different forms or shapes. And the thing what happens is we needed a way to access the data without having to scan full table scan every time. Because that's the brute force way, we full scan all the time, right? We didn't want to have indexes because it would be not very easy to maintain petabytes of a B-tree indexes or other kinds of indexes. projections or joining, whatever you want to call the feature. We didn't want to have a redundant copy of the data that I have to update every time I loaded it, because either I have to do that offline, then the data is not in sync all the time, and there's complications of that, or my loads take longer. We decided, no, you're always only going to have one copy of the data. But if you order that copy in a certain way, then you can take advantage of something that's called zone maps. Zone maps work with any column. It doesn't need to be a sort key of the table, but the way it works is, in memory, I have metadata of every block, of every column, of the whole database, always in memory. So I always know the min and max value of that particular column on that block. So when I query my data and I'm looking for a particular amount, if the value I'm looking for is not between the min and max of that, I don't even touch the block. I don't read it. So I can skip scanning block. And again, it works for any column. So imagine I have a column that I don't have a sort key on that. I have no idea. But if I query for a value that is not present on that value, for example, if I'm looking for a state and I look for ZZ, it's going to quickly say, hey, there's nothing with ZZ there, because the states go from whatever to whatever. It's not ZZ. There's no state called ZZ, right? So it becomes very easy to skip scan, and it's optimal way of using the data. Now, imagine you have a table that is unsorted, and you're looking for a particular date, a particular query. If the table is unsorted by that column, I will take some advantage of that, because I'll have to hit a bunch of blocks, and some blocks I might be able to skip, but might be lucky. On the other hand, if my table is sorted by date, then that same query will scan a single block. That's a huge advantage. Another advantage that we found related to indexes is, if you have an index, and you index the table for example, for the date, like order date, it's sorted by order date or indexed by order date. If you query by ship date, you don't have an index, you do a full table scan. It doesn't help you to have an index on order date. On zone maps, we know that order date and ship date are somewhat correlated, because you can't ship before you order, and normally it doesn't ship a week after you order, maybe a couple days after, right? So they kind of correlated. So if I sort by one of them, when I query by the other one, I still take advantage of the zone maps. So I don't need to index every single column I'm going to ever query. The correlated queries get that for free. So that's another bonus that we found. The other thing we think about on a share nothing MPP cluster is how the data gets distributed. Because if you don't care about how you land the data, I just want to create a table and the system will do that to me, all distributions are even. When I need to join two big tables, I have to cross data across nodes all the time. So the communication becomes a problem. And the bigger the cluster is, the more costly it is to do those joins. So we allow you to choose ways to distribute your data to avoid moving data from one block, from one node to another. So you can distribute your table by a key. You can choose a particular key, and depending on the hash function result of a particular key, it lands on a particular slice of a particular node. And if you have two large tables you join together, and you distribute both tables by the same key that you used to join together, when you join them, the rows that match are already on the same node, on the same slice. So the system can do that and detect that and not have to move data around. Makes for very, very efficient, very large joins that many systems can do if you go all brute force all the time. The other thing, besides the regular even, which is just kind of, okay, I don't know, I don't have a key, I don't have a good key, I don't join this table, fine. We can distribute for you even, fine. It works most of the time if you don't have large joins. But the other thing we added somewhat later was this style all, where we have a full copy of the table on every node. So imagine I have a star schema. I have a few large tables and medium to small dimension tables. You can't distribute all by the same key because the dimensions will have different keys. But if the dimensions are this style all, when I join with the large tables, I'm always going to have a local copy of the table to join, and the system can take advantage of that, and I don't have to move data around. So the goal is to avoid movement of bytes, because it's a physics problem. If I have a petabyte of data, it takes so much to bring that to memory. It's inevitable. It's law of physics. Now, for Redshift, and we launched that, we were great for a few years and adding features and talking to customers, getting feedback, making the product better, faster, nicer to use, etc. And you always go around the fast, easy to use, cheap. That's our mantra. Cheap, easy to use, and fast. We start having customers asking about, okay, but I have a lot of data. It's too much data to load on Redshift. It becomes too expensive to load. I don't even know if the data is valuable. I want to query a little bit, but I don't want to load that on Redshift. It's too hard. It's too expensive, right? Or I have more data, like I need to have 6 years worth of data, but only query lasts 6 months. The data has to be there just to be there. How can I have like a cold version of the storage that stays away from the cluster so I can't have that? So customers started asking us about that. And the problem was their data sets became so large that we had to innovate in behalf of our customers to be able to accommodate their requirements. Now, you can see about how the generated data grows over time and how our capacity to manage that kind of stays pretty much flat. And we have to figure out how can we access that data. I still want to have a ACID compliant full transactional database, but I want to be able to dab into those data that I want to see if it's valuable or not. I still want to do that. So how do I do both? I want two things that are incompatible with each other, right? It's the tyranny of OR. If I want to use EMR, right, it's another product. You can have your own cluster. You can access S3 files directly. You have a lot of flexibility. Direct access data. You have scale out to thousands of nodes, open data formats, et cetera, et cetera. On the Redshift side, I have to load the data. But once I load the data, I have super fast local drive access. I have sophisticated query optimization. I have join optimized data formats. And I have query using standard SQL and optimize for data warehouse. So I have to kind of plan my data. I have to plan what I'm going to do. And it's the difference between getting a car and going for a drive or having on a Formula One team that you have to plan to what you're going to do next, right? And customers have to choose one or the other. Well, maybe not, right? They want sophisticated query, but they also want scale out. They want super fast, but they also want open formats. They want the throughput of local disk, but they want a scale of the size of a whole S3. And that's what we did, right? We did Amazon Redshift Spectrum. It's a way for you to still have your cluster, still have your Redshift database, but you can access very efficiently your data on S3 directly. Exabyte scale. Elastic and highly available. It's on demand. You just pay for the amount of data you scan. Highly concurrent because now you can have multiple different clusters for different departments, all reading from the same core tables without interfering one with each other. And they have their own local tables to match the data with, but the raw logs or raw data generated lives on S3, right? And to bring the data in, to look at the data, there's no ETL needed. You just query it. You just select. Your ETL becomes a select statement, right? And you can still use all the capacities of the Redshift SQL. So here's how it works. And here's like a life of a query on Redshift Spectrum. So you start with a query that is selecting from external table. And maybe the query has local tables and external tables joined together. It doesn't matter, right? It works the same way. You issue the query. The Redshift optimizer on the leader node will look at the query and figure out, do the optimization and figure out what's the best way to access the data, which data has to come from external sources, which data has to come from internal sources. The compute nodes get the compiled version of the query and start running their part of the query. The compute nodes obtain dynamic and static partition information about the data on the external tables, so it can decide which partitions on the external tables to scan. Send those queries. Each compute node can issue one or more different Spectrum nodes to run the query, read S3, collect the data, do the projects, the filters, and the joins aggregations on the Spectrum level, on their Spectrum nodes. Then the data gets sent back to the compute nodes to join with the local tables and the final aggregations, the final sorts you have to do. And data that goes back to the leader node and goes back to the command line. So for the persons doing the query, they don't need to know they're querying external table. They think they're querying a table. It can be local, it can be remote. They don't know. They join to, they don't know the difference, right? It just works. Now, I'm giving you an example that it was recorded on a real-time live, kind of would be like a live demonstration. It's not a real live demonstration, a recording. We record the execution of a very large table, a very large query, very complex query in a sense. And record the execute. It takes about 3 minutes. And I have that time to explain what the query does. Let's see if I can do that. So the video is running, and it's going to execute the query now. So executing this query. So this query is pretty much, I'm joining data from the external table, which is order items, order details from Amazon the last 20 years. And yeah, before I get too excited, right? That's not real data. It's just generated data. Don't get too excited. We're going to find out and join with some local tables how much we sold of Harry Potter books in the first 3 days of sale. That's the query is going to do. But I have to scan all the last 20 years of data on Redshift, or on S3 in this case. We have about 140 terabytes per year for the last 20 years. We have 190 million files across 15,000 partitions on S3, and that's real, that was there. 1 partition per day for USA and the rest of the world. We need pretty much a billion-fold reduction on data process so you can run that on any reasonable time. We did an estimation. That's not, we didn't wait 5 years to see how long it took. Estimation. The same query on 1,000 nodes on Hive without any optimization would take about 5 years to run. That's an estimation. We didn't run for 5 years, okay? Just don't get excited, right? So the first thing to reduce the amount of oil we do, again, brute force only takes you so far. Compression takes the data 5 times smaller. Columnar format makes us scan 10 times less than I would otherwise scan a row-oriented file format. So there's a Parquet files, compressed Parquet files. We use 2,500 nodes on Spectrum to run this query. The static partition elimination reduced to half, and the dynamic one, after the join with those tables, reduced further the partition I have to scan in 350 times. And the query optimizer itself was able to prune data out and columns out during execution another 40 times. So at the end, we have 3.5 billion times to 1 for the execution of the query, right? And the query ran, and the query runs about 3 minutes to scan and return the information about all the sales of the first 3 days of every first edition Harry Potter book. And you see that the joins here, it's hard to read on this resolution, but the joins here is you're doing the joins of the dimension tables to help filter the other table, and all that information gets pushed down to the optimizer. So it's really dynamic way of, depending on who I'm joining is, I know which files I have to hit. So I don't read all the, how many, 190 million files. I'm able to narrow down to a particular set of files, set of directories that I have my data on that I can scan. And let's see if it's gonna finish before I finish talking about this. Come on, 3 minutes. You can do it. Come on, it's a recorded video, come on. Don't fail me now. Let's see where it is. It's almost done. So, there you go. So, and it ran, and this kind of query is, honestly, was not possible before. Without like a huge cluster. This way, any customer can run this type of query and have a ton of data on S3 that don't necessarily have to load to their cluster all the time, right? And it works well for a bunch of different use cases. I'm going to talk to you about that. So it's really fast. I cannot test that, right? It leverages our cost-based optimizer in push-down projections, filters, aggregations, and join reduction, dynamic partition pruning, which is a great feature we added, automatic parallelization of a query against S3 data, so we kind of divide and conquer, and efficient join with the data back on the cluster. And yes, you have a question. You want to wait for the at the end? Awesome, thank you. All right, and it's cheap. It's cost effective. The system will charge you about $5 per terabyte scan on S3. So it's the last. If you query more, to the cluster, you have your cluster, you pay for your cluster, and if you have the data outside, instead of having a bigger cluster all the time, you just pay when you access the data that you normally don't access all the time, right? And you can reduce your terabyte scan by partitioning your data using columnar format and compressed data. We charge over the raw compressed data, not the uncompressed amount, like many other people do. Okay? Now, security-wise, we inherited pretty much all the security credentials we had on Redshift. We have encryption end-to-end, encryption at rest, encryption at movement, and you can have all the same certificates we have on Redshift. Virtual private cloud, we have alert notifications, audit logging for everything, and etc. So it's just an extension of Redshift in terms of how secure it is. It's still as secure as Redshift. And of course, use standard Redshift SQL, right? It integrates the information, have pretty much most of the data points, and the partition, you can partition by any key. It doesn't need to be only date. It can be different keys if you want to use partitions, right? So how you do that? So that's where the confusion starts. If you have tables defined or metadata defined in Athena, we can use that to access the files. No, Redshift Spectrum is not Athena. It's not Athena underneath. It's not. It's a different technology. We develop almost side by side, slightly different goals, slightly different customer, different like requirements. But it's not the same. It's very similar in terms of metadata. So if you have an existing schema on your Apache Hive Metastore, you can just say create the external schema and the name of the schema that points to that, and all the tables are going to show up on your cluster like magic. Or you can create a specific table and you partition by, store it as whatever on your whatever S3 location you have. Right? So you can create a table from files. You don't have to have any Metastore. Or if you have a Metastore, and if you use your data lake thing that you access via EMR, via Athena, via Hive, and now via Redshift, it's all compatible in terms of using the same Metastore. So the support, we support these file formats: Parquet, CSV, sequence, RC files, soon ORC, and soon regex. All these column types, pretty much many types of compression, encryption, different types of encryptions, and no partition tables or partition tables, and the way you define them is how you define the buckets, the names, and directories stuff. So that's the support of Amazon Redshift Spectrum. I have to get used to this name. We've been calling the code name for the longest time, and now there's a real name, and I have to call that name. And no, I'm not going to tell you what the code name was. No. Now, interesting tidbit. We say and we know that you can read CSV directly on Spectrum, but Parquet, compressed Parquet is faster and better. So how I can convert my CSVs to Parquet if I want to keep using that all the time? You can just use a Hive, create table as select, store it as Parquet on a EMR cluster. A small EMR cluster can do that for you easily, and then you can convert your data. Or you can use a Spark, a 20-line of PySpark code that can do that for you on EMR as well. And we have this open source version of it you pick up and use, so if you want to convert your data. It pays off to start like standardize on those file formats that are easier to access by different products. And Parquet become one of the standards of that, and it's very columnar based, it can be compressed, etc. So it's a really good choice. But CSV works as well. Don't get me wrong, CSV works as well. So why if I don't have an exabyte of data? What do? Do I need Spectrum? Can Spectrum help me anything? Well, maybe. First, your data you're going to get bigger. You have a cluster particular size today, and you have to store 2-3 years worth of data, and as data goes by, then what do you want to do with it? You want to delete? You want to remove? You want to make a bigger cluster? You can save money by not making a bigger cluster, get the older data, put in S3, and creating an external table, and then you can still touch the data without having to pay for the data. And normally this data doesn't never get queried at all anyway, so you get that. Right? It makes easy for do analysis for your data coming to S3 without having to actually do ETL. Your ETL becomes a select statement. And it's very helpful to figure out, okay, I have this amount of data on my S3. Is that useful? Before I try to load and organize and figure out the sort key, distribution key, before I can figure any of that, can I just figure out if it's valuable? You can use Spectrum just to do that. And if you find it's valuable and everybody's going to query on a dashboard all the time, then you load, pre-aggregate, and do all this kind of good stuff, right? And you can also improve your availability and concurrency. I have a lot of customers that they have different departments. They have their own tables, but they all want to access a core of tables. So if you use Spectrum for that, you can have different smaller clusters that are easy to maintain and to keep up and to have like ownership. You own this cluster. But they can all access a core data that gets updated for them for a central team. It's a great, great model for them. The other thing that I notice is I have a particular customer where they want to have real-time analytics. And real-time analytics is kind of a misnomer because the only real-time analytics is if you watch the guy clicking the mouse. Right? That's the only real-time there is. You always want to have some time between clicking the mouse, something happened, getting reloaded. And what normally they means is they have to load the database every 1 minute or less. It's expensive to do that on large data. Imagine you have 500 tables you have to load every 1 minute. It becomes expensive. With Spectrum, you don't have to. Your Kinesis stream or any other streaming application can stream the data into S3 buckets. And immediately, real time, you can query via Spectrum. Right away. You don't need to load the database. You can just query throughout the day. And then at the end of the day, you can get the whole package of data for that day, load into the database and do your sorting and distribution, all that kind of stuff, because then for tomorrow, the reports can take advantage of the faster version of the data or to look at like, compare last year with this year, etc. But for intraday data that I need to be available and rarely anybody queries anyway, it's there, you can query, and you satisfy a requirement without having to penalize your infrastructure. You have to have a bigger clusters or more clusters so you can load every 1 minute. So that's one use case that will surprise me when they say, how about doing that? It was a great way of using that for the customers. We had over 20 customers helping us try and fine-tune Spectrum, and I would be very excited to hear how they use the Spectrum on the next reInvent, and some of them might have like something, hey, here's how I use Spectrum to do X, Y, Z, right? Very excited to work with those teams to understand how they're gonna use the system. And again, we're gonna get their feedback, we're gonna make improvements, we're gonna launch new versions, we're gonna get more customers trying, get more feedback, and iterate. We always iterate, that's all we do. So I wanna talk to you about the emerging analytics architecture. Before, we have a particular model where you have your data sources, and then you have the data loaded to the data warehouse, and then you have your reports. What's emerging is actually people are using S3 to store their data. The one true version of their data gets landed on S3 and have one copy there. And they use Glue for a catalog so they can discover and understand that data. Then there's some components of serverless compute so I can figure out the data a little bit. It's a Lambda function or a fire hose connecting data or Glue for a kind of an ETL, or even Redshift, just select the data that's on S3 without loading. And then when I understand and make my data really, really well-rounded, understand the data and can optimize my use of data, then I can load on a data processing unit that can be Redshift, can be EMR, or you can even use Athena to query the data directly. And that's what is happening a lot around our customers. That's the model they want to work on, and we help you. How can we iterate to make that possible, make that easier to do? Because today it might be painful to define the metadata and do data quality or data access. They don't understand. They understand database roles. How do I transfer that to an S3 environment? So we're working through all those changes to make sure that customers can kind of use that. And that's something that we didn't come up with. Customers came to us with that and say, hey, I want to do this. How can you help me do that? I want to leave you with a bunch of resources. And first resource is if you want to know more about Redshift, details and optimizations, etc. If you go on YouTube and look for Redshift, deep dive or Redshift, you're going to have a video of me talking about it. So sorry about that. But you can find a lot of deep dive technical. Our documentation is amazing about Redshift. But the one thing, if you're going to use Redshift, you want to design your table for better use and best access. Zach, one guy that works in my team, created this Engineering's Advanced Table Design Playbook. It's amazing to help you step by step to figure out distribution keys and sort keys for your tables, how to access, how to monitor, see if you're doing the right thing and not thing. And a bunch of those things, we are trying to make it easier and faster for the customer. But right now, we have to offer is those documentations and those playbooks. There is a couple of GitHub repositories for open source utilities for Redshift, admin scripts, views, and a coding utility to help you encode your database, monitoring code if you want to monitor a system in different ways, or even sample UDFs so you can really take advantage of your Redshift cluster. Because we want Redshift to be like a toaster for you, that you just put your workload there, choose a few options, and then it just works. But even a toaster, there's some things you have to understand how it works. Like a toaster has a bagel button. Do you know what the bagel button does? If you don't know what the bagel button does, you cannot use the advantage, right? And later you can ask me what the bagel button does, okay? I'll answer one-on-one, right? We want you to understand enough of the system so we can take advantage of the speed. Because understanding that and use the right sort keys, distribution keys, and be able to set up your data, get you utmost performance. Again, brute force only takes you so far. We want to help you get beyond what is possible by just brute force. We're going to have components of brute force, but we want to do that in a smart way, okay? Thank you very much. Now I'll take questions. I'll take his question first because he was in the middle. Then I will go to you. All right. Yes. The question was if you have to have a Redshift use Spectrum. Yes. And as I said before, Athena is very similar, but not the same technology, not the same characteristics of performance. So if you want to dabble about this kind of access, play with Athena. It's not going to be a lot different. But the technology underneath and how it works is because on Redshift you assume you have some local data and some remote data. Okay? Yeah. 8.03. Yeah. So so the question was that Parcel, which was what Redshift was based off of, Postgres 8.02 or 3, whatever, one of those. And if you think about pushing forward the newer versions, we never did or planned to do a whole, okay, now is in Postgres 9, but there's a lot of features and fixes that we pull from 9 and implement on the 8 because it's so intertwined with the storage engine now that it's hard to do that. Mm-hmm. On Redshift, yes and no. You can resize your cluster, but we cheat. We create a new cluster, we copy node to node in the background for you, and then when we're done, we point to the new cluster. So, yes and no, we cheat. We have that's why the cloud's so great. You can do those kind of things without, like, yeah, but get a few more clusters and move it. Yeah, yeah. All right, a question here. Sorry, the new implementation? No, it's not. No, so the zone maps we had on Redshift is before it existed on Postgres. It's not much different though, but it's not the same. No, it's not the same bits. Questions? All right. Thank you very much. Have a good rest of your day.